All right, so let's look at a few examples of how we can apply the empirical rules into answering a lot of statistics questions here. So really, this example here, it all started out as a data that we're looking at, and then there are a lot of questions that we can answer regarding this kind of data right here. So before I put up any question, let's have a quick look at the data being given in this example here. So SAT scores in the year of 1997. Sorry for using such an older, an out-of-date data. And this data are not truly reflecting what was going on in 1997 for SAT scores, but it's just a figure that I'm using to do my example and demonstration for here. But so SAT scores in the year of 1997 were normally distributed with mean 950 and standard deviations 150. And so once again, the whole idea about this kind of data is that, first of all, notice the plural indicating SAT score. So it's just simply indicating that we're having a lot of data, but we simply do not know how many scores there are. There could be millions of students taking the SAT score in that year of 1997. There could be in the millions, there could be in the tens of thousands. And so basically we don't need to worry anymore about the end count in this kind of gigantic data. The good thing is that it had people who analyzed that data in those years now telling us that the data there were normally distributed. So all SAT score can be placed on a bell curve. And the mean was also found being 950, and the standard deviation here, standard deviation is calculated to be 150. So we already had all that information really that we need in order to do a lot of questions later on. And so now I'm driving into our first question here. But let's say in that particular, according to that data right here. And so the question now says, what percent of data falls between 900 and 1100? And so I should have mentioned that even right before we start getting into the first question right here, when we were still looking at the data itself right here, from now on, after we learn about empirical rules and particularly working on the bell curve, even though just on a very brief preview right now, but I highly recommend now that anytime we are working with a bell curve, so here this is what it is. We're working on a bell curve. We were told that our data is on a bell curve, and we got a mean being 950 and having a standard deviation being 150. The high recommendation here is that we should always draw for ourselves a bell curve. It doesn't have to be a nice, a perfectly drawn one like how the computer can do, but we gotta draw for ourselves a bell curve, similar to the one I have on my table here. So the whole idea of the bell curve, and I should have mentioned as well, this bell curve for now I'm leaving that empty because we're gonna be doing a lot of shading right here. But so on this bell curve, the 0 right here is indicating those values that's right on mean. So, or in other words, you are 0 distance away from mean. Mean is here. Okay. And standard deviation in this problem, note that somewhere the scale is about that big, but the standard deviation here was being as large as 150. And so, and that's all it needs for now. And so now let me get back to question A right here, and that question. So now the question here says, what percent of data falls between 950 and 1100? All right, and so immediately after reading the information given right here, and this time I purposely use a hand sketch version of the bell curve right here, and an empty hand sketch version. And so on this bell curve, to clarify again, but the horizontal line here is indicating all those different kinds of SAT scores. Those to the right hand side are SAT scores above 950, and those to the left hand side are SAT score below 950, below mean. So I'm looking for what percent of data falls between 950 and 1100. So we have done a lot about one standard deviation above mean, two standard deviations above mean, and all that and all that. We don't really have, right at start, when you start getting into solving one question, we don't need to worry about that information just yet. Here's what naturally makes sense right now. All it says is that the data falls between 950 and 1100. And so everything you need is to draw. It makes sense that 1100 is somewhere to the right hand side, and 950 is right on mean. And so that's all you need. And so data falls between is indicating that. I just want everybody to really not worry too much about scaling. So that distance there simply makes sense directly from what happens in the description of the question right here. We want data that falls between 950 and 100 and 1100. And so that's all it needs to get. And so now, once you make the shading successfully, then here's we're going to start doing the next step to make everything become clear over here. So right underneath my bell curve, here's what I commonly do. My low end of the interval, I'm going to take away, I'm going to subtract mean. So this is the low end. I treat that 950 simply as the low end of the interval. But this is truly to reflect my mean. And notice, again, that anytime we're drawing the bell curve, there's a standard deviation should be noted somewhere. And so now that difference, I am going to divide by my 150. So after finish writing that down, I hope everybody recognizes this is exactly the z-score. This is my z-score. And starting on from this video lesson right here, and for the rest of the quarter, a lot of time you're going to see, and at least throughout all of these the discussions in empirical rules, I'm going to use this. So use z-score, of course, is the way to indicate, but I'm also going to use a subscript. The 950 as a subscript right here is just indicating that my z-score here is a z-score particularly for the 950 as the low end of my interval. And so that z-score there, now calculating it, we're looking at a z-score 0. But that's now, remember how we talked about z-score? Z-score measures how far a value being away from mean right here. So this z-score 950 has a z-score indicating 0. So now it's clear that z-score, it's clear that the 950, the low end of my interval, is exactly right on mean, or going nowhere away from mean. And so now along that line, you can see my intention for the next step. I am going to take my other end of the interval, 1100. I am subtracting the mean because getting z-score is the only clear way of indicating how far that particular value being away from the mean. Divide by 150. And once again, this, what we recognize here, this is nothing but the z-score. And once again, I recommend using that good habit of indicate the actual value of that z-score right here. So here I'm doing z-score subscript 1100, indicating it's a z-score for my upper end 1100. Because the reason I'm doing this, because a lot of time in these intervals we always going to have two different z-score calculations. And so 1100 minus 950 divided by 150. So we're looking at a z-score positive 1. And it never hurt to actually indicate the signs here, because the sign for z-score has a tremendous impact in the problem here. But so now that means this 1100, at starts we only needed to think of that as the upper end of the interval. But now seeing the z-score here, it's now becoming clear that we are at exactly in that interval between mean and one standard deviation above. And so now we are ready to find out our picture over here. So let me quickly put you back into the picture I have shown. So we have found out previously, and we've learned how to break the entire bell curve into small pieces of areas like this. And so for our area, it was specifically this area. If we were comparing our drawn picture with the formal area we laid down on a nice bell curve right here, then it's this area right here happening between 0 and 1 standard deviation above. And so we've learned through the lectures that this area is being 34% of data is being inside of that area. And so now it becomes clear that in this picture of owl right here, the shaded area we're looking at, the answer is simply being 34%. And that's how it is. So what's most importantly is that how we got to calculate the z-score that help us. So we start out making a shading to make sense with the question. Simply that's all it is at start. And then the next step is we calculating the z-score. And the z-score, we have a clear indication for us of where to find on our charts the proper amount of area. All right, and the same question. Let's now look at the same example here, but let's now look into a different question. So you can see that the whole data here remains exactly the same. Nothing altered. We've had data being normally distributed. All the SAT scores in that year, a lot of scores, and mean value is at 950 and standard deviation 150. But so now in this question here, what I switched to is now I want to find what percent of data, and you can see that how repeated we have been using that kind of question, what percent of data and falls into a certain interval of data. And so here I want to be between 1100 and 1250. And so now once again, I just want everybody to again practice that good habit right here. But we have an empty bell curve here, again being completely started from scratch for a new problem. 950 is in the center because it's the mean value. Standard deviation of this bell curve is 150. So to start getting into this questions, we don't need to worry about 1 standard deviation above mean or 2 standard deviation above mean. All it makes sense for me at first now is that, and looking at the highlighted area here again, it says all I need is the interval of data that falls between 1100 and 1250. So 1100 is here, and 1250 is just makes sense to be further out. It's okay to be a little bit off scale right here, but whatever the choice that you chose for the scale spacing between mean and that first point, and that's your scale. 1100 is here, and the 1250 is here. Some other value further out. And the question was saying I'm looking for the percent of data between. And so now percent of data is famously or graphically represented as shaded area on the graph. And so now we're looking at that area right there. And so this area here, so now another common and good practice. So now after just simply getting the shading down right here, then I'm going to start calculating my low end being 1100. I am going to subtract the mean value and divide by the standard deviation 150. And always, anytime I'm drawing a bell curve right here, anytime we're working on a bell curve, I highly recommend it to note the standard deviation value somewhere there, and the mean is to be placed right in the middle. And so this is the z-score for my low end of the interval. So z-score of 1100, and that equals this calculation value. And so calculated out, we got positive 1. And then, so now we know enough now that this low end of the interval stays 1 standard deviation above mean. So when we write on mean, remember it's 0 for z-score, but here we are indicating a z-score positive 1 standard deviation above mean. And so I'm going to do the same thing for the other end of my interval. My higher end of the interval here is going to be from where 1250 is. I am subtracting 950, and we're dividing that by 150. And that here gives me a z-score value being a positive 2. And once again, this is my z-score of 1250. And so now we're not only seeing this as a 1250, but furthermore, now this 1250 became clear that it stands 2 standard deviations above mean. And so now we again have learned previously, before getting into this example of hour here, is that this small piece of area on the bell curve, the area that happens between 1 standard deviation above mean to 2 standard deviations above mean here, that area we found through the lecture is to be in a total of, it takes only a 13.5% of area. And so taking that as the reason, then our answer here for this interval, the shading area in this interval is now 13.5. All right, and same example, we're looking into the next question. So question C of this example right here, or basically it's just the third question of the same example. So all that information regarding the data remains the same. We got a lot of SAT scores. All of those scores are on the bell curve. The bell curve has a mean, and at this point, hopefully you're fluent that we always put the mean right at the center of the bell curve. That's why we have been calling mean value the center. Standard deviation is 150. And here the same exact questions. What percent of data falls? But now I switch to a different interval. So let's say I want to be between 650 and 1100. And so once again, from start, here's your empty bell curve again. A hand sketch version is perfectly fine. Mean value is right in the middle. Standard deviation being 150. So my interval is anywhere between 650 and 1100. So once again, we just simply need to draw the interval, and without too much worries about how far it is in terms of how many standard deviations. We do not need to worry about those yet. All it makes sense to me is 650 is somewhere to the left hand side, and somewhere to the left hand side 650. And then the other point is 1100 was already known to be above mean. So here we have that kind of interval. And like I said, even though we don't, and we still don't have to worry about how far the scaling is, but you can see that it naturally makes sense enough that as far as the distance, 650 to 950, you can see that it's about twice as long as the distance from 950 to 1100. So that's how I can kind of reasonably put down my 1100 here relatively to the scale how I set for my 650. But it all came out from just natural math that the distance from 650 to 950 is longer than from 950 to 1100. But in the end, we still don't need to, really. We don't need to get that far details about exactly how many scales away. But now, ultimately, for the question, this is the area shaded completely from anywhere from 650 to 1100. And so for this kind of problem, I just want to point out for everybody that it, according to your shading, it now starts to give us a plan here. But you can see that this interval, this area has the center inside of that. And so if I now really draw the center a little more trivially here, a little more clear here, then you can see that it's a combination of these two pieces of area. Or you can, or maybe I'll save that thoughts for a little later. But so now, once again, the next important step again is to understand that we are going to do (650) minus 950 divided by 150. Value of the low end minus the mean divided by the standard deviation. That now gives me -2. But this -2 is truly my z-score of the low end. So I'm indicating that with a subscript z-score of 650 equals -2. So now we know that 650 here is being 2 standard deviation below mean. So that's what we know now. So now back to what I was about to say earlier. So now once we're clear about the lower end of the interval being the lower end of the interval being 650 is also being at exactly 2 standard deviation below mean. Here we can now start putting another point about exactly midway between that and between 650 and 950, and that point right there is the point being 1 standard deviation below mean, and we can kind of make a dotted cut here as well, so that we can use that for some further explanation later on. And then again, 1100 as our upper end of the interval. I am going to subtract 950, my mean value, divide by 150. My z-score here comes out being positive 1. And so z-score for 1100. And so now after seeing z-score, now I am clear that 1100 stays exactly 1 standard deviation above mean right here. Alright, so now after you seeing that clear picture with all the proper notation here, then it looks like our total area we're looking for here came out from a accumulation. Now I got to use that term accumulation because we got more than one pieces of little areas. So there's a piece here between -2 and -1. There's another piece here between -1 and 0. And those -1 or -2, they are indicating how many standard deviations away from mean right there. But so we got 3 little pieces of area. So to find that area totally, to find that total area being shaded here in our picture, I am going to look back at this diagram again, and this graph that we've done before. But so this little piece here we've calculated that to be a 13.5. This next piece here that I'm shading slightly differently to really indicate that we got separate little pieces of area. But that piece here is a 34%. And then our problem, the area extends to as far as this other piece as well. So this other piece is also another 34%. My math now is clear, coming out to be the amount of shading area we're looking for being a 13.5 here, 13.5%. After looking at that chart here, now we're going to add, we're going to accumulate together with that 34% here, and we have another 34% here. And of course, it's never bad at all to rewrite into your hand sketch picture here that this is a 13.5%. There's a 34% here in this area. Okay, and there's another 34% here. Okay, and so now altogether calculation comes out being 81.5. All right, and then same problem, same data. We have a different example question right here. So this time the question is asking what percent of data falls between 500 and 800. And so once again, just starting out from scratch right here, and here's my empty bell curve again. I am ready now to put down my the low end and the high end of my intervals here. All it makes sense here is that 500 is really further from 950 compared to 800. So I'll just put it here somewhere. Okay. And then 800 is somewhere here. And that's all it needs right there. That's all it takes. And so the area, the question was asking for what percent of data falls between. And so now the percent of data falls into an interval of data. We refer to that graphically as a shaded area. And so there you go, you have another shading area to be found right here. And so once again, once you got the area sketched and shaded, all we need now is to find the z-score. So 500, take away the mean 950, and dividing that by the standard deviation is 150 right here. My z-score comes out being negative 3. And that now indicates that 500 stays 3 standard deviations below mean. And so this is the z-score of 500. I am going to do similar work for the upper end of my, or the higher end of my interval. 800, from where my value stands, I'm going to subtract 950, and then I'm dividing by 150 for here. That gives me a z-score being negative 1. That is z-score for my 800. And that here, now it makes it clear that 800, my higher end of the interval, stays 1 standard deviation below mean. So once again, we had that interval now being clear, that we know how far each of the ends of your interval is being away from the mean in terms of how many standard deviations. And so if you worry about, is this distance here exactly half of that distance, it's not really the point here. But I mean, theoretically it needs to, but we can't blame ourselves for being a little bit off from the scale right here. It's completely okay. But now you can see that from 3 standard deviations below mean to 1 standard deviation below mean, we have another special point right exactly halfway. And so that point was the negative 2 standard deviation, indicating 2 standard deviation below mean right here. So now I'm going to create another sort of like a thin cut in between. And so obviously my area totally that I'm shading here can be broken down into 2 smaller pieces of area where it can come directly out from our graphing picture. All right, and so what we found further as a reminder is that this little area from 3 standard deviations below mean to 2 standard deviation below mean, that area we already found to be a 2.35% in that little interval. And we found further that this other interval from 2 standard deviation below mean to 1 standard deviation below mean right here, that other interval, another separate little piece of area, being a 13.5. Now we know that, so this total area we're looking at now is going to be just simply the accumulation of 2.35 accumulated with 13.5. And our answer comes out being 15.85. And here my next question in the example is, so what about what percent of data falls above 1400? And here I'm changing the wording a little bit, so allow me to highlight again. So far throughout those past questions, we've been looking for interval between a low end and a high end. But now we have a different kind of interval here. The wording says above 1400. So back into my hand sketched version of the bell curve, and another empty bell curve being indicated here. So 950 is right in the middle. So 1400, once again, naturally makes sense enough. It's just higher than 950, so we're going to put it to the right hand side somewhere. And now the question is asking the data, the percent of data falls above 1400. So as far as the shading, all we have to do is to create a shaded area to the right hand side, because that's the way how we have been understanding about numbers. Numbers falling above a certain other number, and that means we're going to be considering all of those to the right hand side. So now that's the area we're looking for. And then once again, I still don't need to worry about how many standard deviation this value is. All it makes sense to me, to any of you viewing this video, is that 1400 is to the right hand side of the mean, and then we're shading to the right hand side because we're looking for the amount of data, the shaded area above 1400. And so, and then to get clear, to nail it down to standard deviations and all that, then I'm going to calculate. And here in this problem, notice we only have one value ever. Yes, let's calculate the z-score for that value. Z-score of my 1400 equals, my work here is going to be 1400. I'm subtracting 950 and I'm dividing by 150. My standard deviation on this bell curve right here, previously noted. And so what I found now is going to be positive 3. So now it tells me that my value 1400, my only one end of the interval. So where's the other end? It's sort of an infinite interval over here. The other end doesn't have a finite stop. So all I know is my interval starts at 1400 and keep shading further to the upper value and the upper values. But now, as far as I know, this 1400 now is at 3 standard deviation above my mean value, and mean is permanently at 0 standard deviation away from the mean. And so now once we got a clear understanding about how far this lower end of our interval is, or thinking of an area, it's a cut again. And so looking at the chart we have built right here, then 3 standard deviations above mean is here. And so the area that we drew equivalent to this much shading, and like it's above means all that accumulated tiny tail to the right hand side of 3. That's all we're looking at. Yeah. And so our calculation previously throughout the lecture was indicating that this area here takes 0.15% of the entire curve area. The whole curve area permanently 100%. So, but that little tail here takes only 0.15% of your entire data inside of that normal distribution curve. And so now, coming back to this problem with the hand sketch illustration here, then the answer became clear. All we need to say now is that that answer, that shaded area, has to be 0.15%. And this is our last question in this entire example right here. But so now what about same exact bell curve? But we're at the question says we want to find what percent of data falls above 1100 or below 650. All right, so back to my writing board here. And here's my empty bell curve again. And so for now, we don't need to worry too much about what it means by being above and or below, but let's put down successfully these two numbers first. And don't worry about shading yet. 1150, what makes sense? It happens to the right-hand side of your bell curve. That's what it is. The other value, 650, is about here. And experience now, at this point, experience can naturally tell you that, and you can tell that 650 should be further distance from 950 compared to where 1100 distance with 950. So that's why I'm drawing my 650 further on the left-hand side right here. More distance compared to 1100. But now once you put down the two values, let's put in the other information. The question says I want above 1100 or below 650. Now, as you enter this course, you must have done some basic algebra. It doesn't have to be too much, but you have done some basic algebra, and it's the idea now is that above 1100 or below, that statement or right here means we're gonna draw a shading that we're gonna have two broken pieces. One piece will be shaded to the right hand side of the data, and another piece being shaded to the left hand side of data. So this interval we're doing here is indeed two separate intervals. We want to consider those score above 1100 or below 650 right here, and that's why we created a drawing where we got two broken up or two disconnected areas right here. And so here's how I'm explaining this concept right here. Now, some point later on, you will see this kind of situation when we will be formally working with the bell curve, the normal distribution. So the situation like this, where your area got broken up into two separate areas like that, a lot of time it's just my term that I call this kind of problem is the disconnected. We got area being disconnected areas. It's just really my term, but it indicates the fact that it's not one area that's going all the way through, but there's a piece here and there's another piece there. So the situation like this, later on when you work on a bell curve formally, it happens a lot. And so I refer to that as disconnected areas. Okay, so what about this? Well, and before we can get further, once again, we have to calculate z-score for all of these values, because they will get clear with us in terms of how many standard deviation this guy stays below mean, or how many standard deviation that other guy stays above mean right there. And so here I'm looking at, so 650, subtract my mean 950, and divide by 150. My z-score, and this is z-score for 650, it comes out being -2. And then I'm repeating again for my other, repeating the z-score work for my other value. Z-score of my 1100 equals 2. So here's my 1100. I'm subtracting 950 and I'm dividing by 150. And this gives me a z-score being +1. And so, and anytime I'm doing a bell curve problem, I always have a designated area separately to calculate all the z-score. And so now, getting the z-scores nailed down, it tells much better information that now 650 is 2 standard deviations below mean, and 1100 is 1 standard deviation above mean. Right? And so allow me to give some lengthy explanation a little bit. But so now one of my area is here, but it takes 3 little areas involved in it, included in it. So from 1 standard deviation or above, there's this area between 1 standard deviation and 2 standard deviations away, and additionally combined with another, accumulated with another area between 2 and 3 standard deviations, and then all that's beyond 3 standard deviations. So in other words, above 1100 is the same as accumulation of. So this piece here between these two, we already know being 13.5. This piece right here between 2 and 3 is 2.35, and this very last piece here is a 0.15%. And so totaling up all of that, the calculation says 16%. So 16% is all that accumulated area to the right hand side of that 1 standard deviations interval, but to the right hand side. And now the other area is from 2 standard deviations below mean but shading to the left cumulatively, and that means we have this little portion and additionally another, all that remains beyond -3 like that. And so our calculation work we've done through the lecture we already know that this area here between 2 standard deviation below mean and 3 standard deviation below mean, that was a 2.35%. And then the other area here extending to further left and then completes out the left tail of the bell curve there was we already knew through our lecture being 0.15 here. And so now totaling up these two areas to get our complete accumulated area on the left of -2, then calculation shows we're looking at a 2.70. $2.5. And so now we are ready for putting all the pieces together. So in the end, my total shaded area combining the two disconnected areas together, what we had there was 2.5% from the left area here, and there were a 16% of data on that other area right there. So all we need now is to total them up, and calculation says we're looking at a total of 18.5%. So I need to make a last note about my entire example that I was delivering here. But as you watch through my video examples here, then some of you viewers out there, and especially students in my class, you might wonder, why am I going in on each of these example questions, why am I using such a slow method, such a method that's so slow in the progress? But the aim of my video lessons here, the aim of my method here is to aim at the viewers, at the students who have the least experience in mathematics. So for example, say, what I need to clarify is my way, how I taught here, my method here was not the only method. And I'm not saying that it's the fastest method. It's just say, for example, in some problem, like say, in the last problem we had, we were looking for the disconnected area either above 1100 or below, maybe I draw a little too small for 1100, but above 1100 or below 650. So admittedly my explanation took a long process to get the answer, but the point here is that I need to ensure even the viewers with the least experience in math can nail it down and arrive at the correct answer. But for any of you viewers out there who already had a good experience in math, and especially the students currently taking my course in statistics right now, and you already have done some good amount of math background, then my way I approach this problem, you obviously notice it's not the only way, and it's not the fastest way. I can quickly point out as another way to approach a problem like this is that you can quickly calculate how much area that is in between here and here, and that area there is that area there itself is, let's say here it's a 47.5 here on the left, and then there's a 34 here. Okay, so all together there it takes an 81.5% inside of that empty area. So quickly we can arrive to the final answer, accumulating these two separate disconnected areas by doing 100% of the whole curve. And the reason I mentioned about this style is that later on when we get into other kinds of problems, then applying this style can also be quite useful sometimes. But the area we're aiming at is being outside of that empty interval. So just 100% whole curve, full curve, and subtracting out the 81.5% from that. And that comes out equals 18.5% as agreed in our example that we finished. And so my point is, being the teacher here, I'm just simply choosing the method that even click for the students, the viewers who have the least experience. However, you are more than welcome for any of the students out there, or for any of the viewers out there who already had a much better experience in mathematics. Then you are more than welcome to explore other ways that can work a lot faster. All it matters really for this type of problem is we be able to get our correct answer.